You can start.
Okay, nice. So this presentation is about it's a continuation from my postdoctoral in Brazil. It's a collaboration with CEMADEN. CEMADEN is a National Center to Warming and Monitoring Natural Disasters. It's near São Paulo, the city of São José dos Campos. And we will talk about a method to predict rainfall nowcasting using deep learning method in southeast of Brazil. Yeah, so historically in southeast of Brazil has been very affected by flash flood. São Paulo and the city next near São Paulo, for example, Campinas and the other cities. And this type of event is very difficult to predict because it's very quick and it is very located. So the aim of this study is try to answer these questions. So can the latest rainfall observation measured by weather radar help to generate rainfall nowcasting? And what is the capacity of deep learning methods to forecast extreme rainfall events? So to try to answer these questions, we generate short-term rainfall nowcasting using the LSTM method, considering convolutional recurrent neural networks. So the study area, it's in Campinas city. We can see it's the blue shape. It's near São Paulo. The city is like 1 hour from São Paulo. And the red point, it's the radar. So the area that we consider it's 60 kilometers square from the radar where the radar is installed. So the radar, the radar is 1 kilometer square, and we have a new image each 10 minutes. And the period considered in this study is 2016 and 2007 years. For this study, we selected extreme rainfall events. So for that, first, we consider a threshold. So the events start when the 5 millimeters per hour exceeds, and the event finished when the threshold is less than 5 millimeters per hour. So this was the first step. After we try to look in the median and the website, try to find the news from these events. For example, if there was something damage or something talking about these events. So it was 12 events. We selected 12 events, and the duration which was between 5 hours and 1 day, 12 hours. And the pixel maximum accumulation, which was between 83 millimeters to 282 millimeters. So it's a nice variability. And we use these events to train and test our method. So for that, the method, it's a deep learning method. We considering neural networks. So in this case, we use the LSTM algorithm. And why? It's because this kind of recurrent neural network, considered there is gates, and the neural networks can decide which information it's nice and it's important to save, and which information it's okay, we can forget that. And it's nice this kind of method because the flash flows, it's the last information is more important. So these gates can consider the last informations, give more importance for the last image, radar images, for example. So to explain better, we consider it 4 layers convolutional neural networks, and one layer convolutional 3D. And why? It's because we try to, in the convolutional, we try to take in account just the more important features. And when we say kernel 3, it's like in between 3 pixels, we try to take just the most important information. And the neural networks try to understand the historical data to predict this kind of event. So how we train the model? It's considering sliding windows. So here we consider 2 types of sliding windows. First one considering 5 images, and the second one is 7 images. And how it works? For example, we consider 9 events to train the model, and we separate 3 events just to test the method. So 9 events, we take into account for example, every 5 image is like a movie. We take 5 image and give to the model. After we change now the slide window, we take into account 5 image. And we did that until the last information of the event. So we can see that in the figure. And we did the same considering 7 images. And the end, it was 883 series of images, like 883 movies that we give to the model to train and to understand how these events work. Okay, to evaluate this method, we consider it 3 events to validation, and the persistence prediction. The persistence it's the last radar observation. And to evaluate it, we consider the area of the rock curve and considering different thresholds. Here is just an example. We consider we predict 8 minutes forecast. Why that? Because when we look at these events, the temporal correlation, which was maximum 1 hour and 20 minutes. It's like after 1 hour and 20 minutes, it's nice. It's like a new event. There isn't a correlation between the last images. So we can see, here's just an example. We can see the prediction can take the rain zone very well, and sometimes it's overestimated, the intensity of the rain. So here is the results considering a threshold like 1 millimeter per hour, the threshold for the rock curve. So in the graph, in the figure, we can see the x-axis is the time steps, and we can see until 8 minutes, there is a nice prediction, considering both methods, 5 images and 7 images. And the prediction is better than this persistence. Okay, the 1 millimeters per hour is not so high. So we try considering 5 millimeters per hour. And here we can see the same. Both methods is better than the persistence. But after 60 time steps, it's difficult to predict this kind of event because the rock curve area is less than 0.5. Okay, but when we look both methods, we can see there isn't a lot of difference. It's very near the results. So we can say both methods have a better, best precision considering the persistence. The M7 image method show more satisfactory results, but it's very near. There isn't a lot of difference. And we think that this approach can help to nowcast the extreme rainfall events. But we consider that we need more events to train the model and to take into account better the intensity of the rain. because sometimes it's overestimated or underestimated. And future works, we want to create perturbations in the forecast model, considering rain gauge data, and to generating simple rainfall nowcastings, like taking account the difference between the radar data and the rain gauge data, and also train the model in the different situations. For example, considering train the model just considering extreme events that has more variability, and taking account of different events. And also, this prediction we use is like input in the flood model prediction based on a neural network. It's another project that it's a master study, and they try to generate flash flood forecasting considering using deep learning methods. So I think it's that. Thank you very much. And I don't know if you have questions.
Thank you very much, Angelica. I have just one quick question before I open the floor. Why do you have smaller lead times with the higher threshold of 5 millimeters per hour? Why does it shrink from 80 minutes to 60 minutes?
Here, or you say why there is
yes. Because when you have the threshold of 1 millimeter per hour, then your model is better than the persistence until 80 minutes lead time. But then when you go to 5 millimeters per hour threshold, you have a 60-minute. You're good until 60 minutes only. Why does it change with the threshold?
Yeah, I think it's because it's more difficult to predict when there is when the intensity is it's higher. It's because when we saw the results, the model is very nice to take the rain zone, but to take the intensity is very difficult. I think it's because the intensity change a lot and very fast. So yeah. And we try also considering a threshold like 20 millimeters per hour, and it doesn't change a lot. After 1 millimeter per hour is like similar.
Could that be also because the persistence would be better also for higher intensities, maybe? So
yeah.
Okay, thank you. So I invite all the speakers to turn on your videos, and you can ask questions to Angelica, and I will also read some questions of the chat now, and then it will be for all of you. We have questions for all of you, but first, if you have any other question for Angelica first. Angelica, if you want to unshare your screen then, so that we can see everybody.
No.
Okay. So from the chat, I still have one more question for Angelica. Unfortunately, it's anonymous. The person didn't put his name. In addition to the rock area, should you consider other verification metrics? For instance, rock does not measure systematic biases.
Yeah. Yes, we will consider to take into account the mean absolute error, for example, and taking account other evaluation metrics.
Okay, anyone else like to jump in?
Yes, I have a question for Angelica.
Yes,
Can I? Yes. Angelica, I was wondering if you I don't know anything about machine learning, and I may confess, but can you use synthetic data for training? Suppose you simulate a lot of rainfall scenarios and rainfall runoff answers to these scenarios, many possibilities, and you use this to train. And then at the time of forecasting an event, you feed the model with some more updated information coming from radar or anything else. And then he can just select it in this past training full ensemble of possible scenarios to improve your prediction?
Yes, we can do that. There is a generator. We can generate, how can I say, new data, taking account the features, the information from the real data, but we don't know how we can do that yet. But yes, we can do. I don't know the details how we can do that. But like, for example, taking account just 5 events and generate new images, just considering the best informations. But yeah, I think it's we can do. Yeah, it's possible. And this is a very nice idea because in this case, we can have more data to train the model and to test after.
Thanks.
Thank you. Since Elena, you are here with us, I have a very upvoted question from Juliano Fink. He says, nice talk, Maria Elena. Do you think the difference between the forecast peak and the observed peak is mostly due to the quality of the ensembles? Since the water level got over the historic record, this is probably leads to extrapolation from the rating curve as well, right? So that, I think the other speakers will also have something to comment on it. But please, Elena, what do you...
Oops, sorry. Yes, so I think that in the case we studied at the old river in 2018, we have a problem with the quality of the ensembles, and in the sense of having the right timing at the right time, the right quantity of rain in the right time, or at least more or less the right quantity of rain the right time. Then we have just checked on observed points where you have one fixed observation which may contain uncertainties, but we haven't evaluated it. And we also checked at non-engaged points where we have these high max estimations that are from post-survey analysis, like Marco described it a bit. And in these estimations, they have already some uncertainty around in terms of magnitude and timing of the peak flow. And we expect that at least some ensembles will come inside this box. And we are not even talking about how many and the probability, which is another level of accuracy that we need to work with, the probability accuracy. So I think that we have both cases. In our case study, it was effectively a matter of getting the right timing and the right quantity. So the model is not producing water peak flows for the bad reasons, I think. So in our case, it was that, but it can be also observation uncertain for sure. But I think the ensemble uncertainty is today probably greater than the observational uncertainty for these cases where we have some flooding, but not that much to disturb much the peak flow estimation.
Okay, thank you. And for Linda, if you're still there, I have a question from Sarah Dance. She asks, you mentioned needing to understand the believable length scales of the forecasts, and which tools are available to this, if any?
Yeah, it's a good question. I think it's depends on how long in advance you're trying to use the forecasts and whether there's any tools to assess that. I think this comes back to some things someone said earlier about needing more robust event-based reviews of events so that we can, understand more about what we can learn and how we can then use that in the future to inform our understanding of how reliable the forecasts are. So I'm not immediately aware of any tools available to assess that, but certainly something that is needed.
Okay, thank you. And there's one question for Darren from Clemens Zimmers. He asks, must N be a constant as long as the riverbed does not change?
Well, that's a good question. Of course, N does vary with depth, but what's happening in these indirect methods is that n is assumed to be a constant. So it's very simple. So that is another reason why I think it's quite important to have some reality checks on these indirect estimates of flash floods, because in most indirect flow methods for flash floods, n is assumed to be across depth and across the section. So it isn't in reality, but often in the techniques it is assumed to be constant.
Okay, thank you. I still have a couple of questions for Maria Elena about your model, the model that you used. So Leandro Kazimierski, he's asking if you're using hydrological data for data assimilation in your different runs, basically.
Okay, we are not assimilating discharge data in our semi-distributed model yet. There is some work ongoing, so all the results I showed you are without assimilating discharge data, real-time discharge data, let's say. But of course, we are assimilating the precipitation, observed precipitation at each time of the forecast. So we launch a forecast after updating the states of the model with observed precipitation, but there's no assimilation of discharge data yet.
And Clemens Simmers asks also if you use ensemble of hydrological model, like different parameters, in addition to the precipitation ensemble.
No, we haven't. We haven't used that, just the precipitation ensemble.
So you just calibrate and you have one set of parameters, right?
Yeah, we calibrated before the flood event that we were analyzing. So we use only data before the event. We are not even including, I think we are not including the event. But, and then we run the ensembles with the meteorological ensembles only.
Because you were saying that the model can very well capture the winter events, spring, and also the summer events. So I was also wondering if there would be different parameters to adapt to these different conditions. But no, it's the same set, right?
Yeah, there is this adaptive option we put in the model is in the production function, and according to the rating of fill rate of the reservoir, the production reservoir, and according to the intensity of the rainfall, it will react different. It will produce net precipitation differently. But this is internally in this structure of the model. The parameter doesn't change, and we are not. The parameter is the same calibrator of the whole year. We are not separating per stations. I'm not in this case. I'm not really sure that using different sets of parameters would enhance something. I think that it would spread a little bit more the ensembles, but it still would not completely solve our problem, let's say.
Okay, thank you. And now I have a question from Harry and Hendrix Fransen, and was posted as Maria Elena, but I think Linda could also comment on it. From your historical records, what is the trend of predicting flood peaks? For example, do you observe a reduction of relative error in the flood peak? So he says error goes down from 20% in the years 2000 to 15% nowadays. And is there a systematic evaluation of changes in the forecast's quality overall?
I think it's a very, very good question. And I don't have any evaluation of how much we have improved in time. And meteorologists do that more often than we hydrologists, I think. So they say how much lead time we gain, for instance, by improving the models in a decade or in a couple of years. I haven't done that, and I think that this is probably because the changes in time are more in the how we predict the precipitation than how we improve our hydrological model, I guess. So, but I think it's a very good question for holistically for hydrology. How much for hydrological forecasting? How much are we improving in time? in our models, in our methods. I think we are probably improving more the way we communicate with meteorology, we couple with meteorology, the way we couple with our impact with our users, than the way we are just simulating or predicting differently inside the hydrological models, let's say. That's my personal opinion. But I think it's a very good question. We should try to get some community answer for that. That's nice.
Yes, sure. I think I read a paper recently about this, but for meteorological, how it evolved very quickly when we have very nice, a huge evolution lead times, and we could do this for hydrology as well. Linda, do you have any comments on this?
I got lots of comments on this. I think in terms of how we can assess quality, we need to understand what we mean by quality. Do we mean the scientific quality of the forecast, or do we mean whether people have communicated it and taken action on it? And I think if we look at how we forecast and communicate these type of events, we have definitely improved. We can see we kind of have longer lead time. We might be able to issue alerts a few days in advance saying a big rainfall event is coming, be prepared, and people are better at acting on those forecasts. So that's a success story in terms of our communication. But again, yeah, I'm not sure that we are as good as the meteorologists in assessing quantitatively what we've done. So yeah, I agree with you that it's something that we should look at trying to quantify a little bit more. And that would help build trust in our models and our assessments if we could say to people, actually, for this type of event, our forecasts are really good and you should therefore act on them straight away. That would be really helpful in the communication chain. So something I think we can do more of, and it's definitely important.
Thank you. Anyone else would like to comment on this question? We could try to write something together and afterwards then maybe. Oh yeah, I have still a question. No, I think we went through all of them. So here in the speakers room, do you have any further questions to each other or about these themes that we were discussing? Oh yeah, I have one question here from Christian Schwala to Maria Elena. Any idea why the spatial patterns for the large ensemble of 80 members was so different from these smaller ensembles?
I think yes, I think that it comes from the way they built this big ensemble. So they added perturbations. So they had the smaller ones were numerical weather prediction model, and then a second one with numerical weather prediction, two numerical weather prediction models combined, the deterministic ensemble. So combined in terms of time lag, let's say, and then the third one with more members, 90 members, I think, was built with stochastic perturbations of magnitude, location, and things like that. So if we look at some rainfall fields, we can see this kind of large patch of rainfall in this bigger ensemble because you have more ensembles, it moves, so you aggregate, and then you see that large patch. So I think that's the point is it's more in the perturbations, I think, that makes the difference. What we have seen is that it's not necessarily the best one in terms of you add perturbations, we add spread, but we still have the same form problems, let's say. So same timing or like form of the rainfall falling over the catchment that is double peaked or peaked a bit earlier or later than the observed ones. So you add perturbations, you add spread, but you do not necessarily add information, so different information. So that's what happened with our experience. But I think that all this is very much related to the way you add these perturbations to the fields. Maybe different ways of creating perturbations could give different options. But I also think that it's quite difficult to find how to do that, because it's mixing statistics or statistical post-processing with physical outputs, or outputs from physical models, let's say. So which kind of, you can create more problems than solve them in some cases.
Okay, thank you. I'd like to ask now Marco about a little bit about your talk today, and also the one that I saw in the EPEX webinar. If flash floods are still hydrological black swans, because we don't have enough data on it, how to deal with this scarcity? Should we, as the research community, really invest more on data collection from field campaigns like Darren presented, or crowdsource insurance database? How can we deal with this from now on?
Well, this is a good question for sure. Actually, we did a lot collecting field data on flash flood. And I would say that not that much of that research really transposed to improvement in hydrological model or improvement in the hydrometeorological forecast and warning chain. I think that we should invest more on trying to use this data to improve our tools, and also use this field campaign in order to cross-source data together by using methods from citizen science in order to also use these opportunities to communicate better with the public on what we are doing on these rare events. These are rare events, but which happen more frequently now in larger regions.
Okay, thank you. So you mean, that this data collection would also help us communicate better with
Exactly.
people, yeah. And Darren, do you think, as a practitioner too, do you think this is the way to go, that this is what is missing the most now to improve our forecasts?
Well, I don't know. I mean, I sometimes think we get a bit lost in models, really, without going back to data a lot. I mean, I think that's a general thing in hydrology, really. I mean, recently I've been working on quite a lot of work related to Earth observation in different fields, some of it related to water. And I always feel that sometimes, I'm trying to be careful what I say. Sometimes there's a disconnect between the modelers and the data collectors. I mean, I think that's always been the case. So I don't know. I always think that more data is better, and it's always good to try and gather more data, really, and see what happens on the ground. Sorry, that's not particularly articulate or insightful, but anyway, those are just my thoughts.
Thank you, Darren. I have a new provocative question from Clement Zimmer to the whole group. What about putting meteorology and hydrology into one integrated model in order to better learn from each other, or to improve flood forecasts? So anyone, Elena, would you like to start commenting on it?
I think that putting people together is always a great idea. Now, I think that what we have seen with the models, that we sometimes complain that the meteorological models, the Earth system models or land surface coupled models, do not do the water balance well. So it misses some volume of water, which are important for the users at local users in aside the river. And we complain that the hydrological models are not doing the energy balance well, and so on. So I think that I think that putting them together is very nicely. I'm not sure that meteorologists would work with our simple hydrological models very well. And I think that we may be too small part in a meteorological chain of models, the hydrologists, and we may lose the link with the local user, with the local, what's happening locally in the river basin, just beside the rivers. Because when we see meteorological models doing hydrology, it's almost compared to simulated discharge, not to observed discharge, because of all this, of course, all that we need to take into account in the land surface in terms of process and modeling and so on. So I think it's a good idea to put them together. I'm not sure that our models as they are today, I'm talking about the meteorological models and the most operational models in flood forecasting, they have entirely capacity to talk and to communicate through all the scales that are of interest and through all the complexities that we have in the land management scales for hydrology. So I think that keeping some local models running with local expertise in hydrology is quite important also.
Yeah, that would be.
Can I just comment on that
Yes, please,
as well?
please,
I mean, I don't think it's just a matter of modelling. I mean, I think to a certain degree it happens anyway, bringing models together. I think what's useful and what's happened in England is that National Flood Forecasting Centre, and that's staffed by both members of the UK Met Office and members of the Environment Agency. So you're bringing the two different experts together. You're bringing the hydrologists and the hydraulics and the flood forecasters together with the meteorologists. And I think it's not just a question of linking models. It's a question of bringing different people together and working together. And that appears to work quite well, where you've got these two different sets of experts working on a flood forecasting centre 24 hours, 7 days a week together.
Yeah, I'm thinking about maybe just, it's not to take into account the prediction and numerical model from the meteorologist, but try to take into account, for example, the features and from the weather and from the hydrological features. And for example, try to combine these informations in a new model, maybe can help to give a better prediction. For example, in machine learning, there is sometimes people try to do that, but I don't know in this issue it's possible, but it's nice. I think it's nice. It's nice to try to take into account these features from different model and parameters. Yeah.
Yes, about this machine learning and everything. I also have another question from Leandro Kazimierski from Argentina to Linda. Do you think surrogate models generated with neural networks from urban hydraulic models with observed and synthetic simulations could be a good approach?
Yeah, so this is something I've been asked a couple of times over the last month or so. So clearly it's an emerging area that people are really interested in. I have to admit, it's not something that I know lots about. It's not something that I'm aware of that's being used operationally in the UK, at least. So yeah, potential there. I don't know, but I definitely think it's something that could be useful, and it certainly cuts out some of these issues around computational time. But then it comes back to our discussion about, have we got enough data to train the model on to make sure that it's representative for the type of events that we're going to experience. So yeah, potential, but there's some learning to do, I think, and some demonstration of capability, which will be really important if you want to use a different type of a model with kind of operational end users, because they can be a bit skeptical about new ideas. So it's really important to demonstrate the strength of something strongly, and then obviously then it'll be like, yeah, that's great, let's go ahead with that. So I'm something I'm interested to see more of in the future, to see whether it answers some of the questions.
Okay, thank you. And you presented us a very broad view of the whole chain. Where do you think still really laying the main bottlenecks actually for the nowcast precipitation, for the nowcast precipitation, but also flash flood nowcasts, and also to societal applications, so that it's really useful the bottlenecks for you, in your opinion? Where are
So
them?
you're saying, where should we be putting in our effort to make the whole thing more effective?
Exactly,
I think
yes.
that's the question there. I think that's really difficult to answer because a lot of people have got different opinions, and a lot of it depends on where you're coming from, whether you're a data person, a modeling person, a communication person. I think it feeds back to some of the discussion we're saying here about if we can increase communication between hydrologists and meteorologists, have better understanding of what each group of people is doing, understand more about the uncertainties in the model, then we can make better use of the science that's currently available. So rather than continually trying to develop new things, actually, I think if we all spoke to each other a bit more and understood a bit more about what each other's models are already capable of, we could make really effective use of them and have some kind of quick wins there, which should be beneficial to everyone, rather than saying, oh, we need another 5 or 10 year research project to look at this. Actually, we can do something better next month if we just work together a little bit more, would be my opinion. I know other people have got different opinions.
Yeah, I was wondering if Marco, Darren would think that more than modeling, we would still try to collect more data to be able to progress in this field. Do you think?
Well, I mean, I always think, you know, that what everyone tells you, the hardest thing is what Linda said, is to get the right action for the warning. And, you know, as technicians, sometimes we get this is my opinion, too wrapped up in the accuracy and the skill of the forecast, which is important because you want to have an accurate forecast, but without trying to see what the limitations are of the communication. And, you know, the communication issues are the same, in my experience, everywhere in the world, whether you're communicating floods or you're communicating diseases. Decision makers and people often find it hard to deal with probabilistic forecasts. That's not to say that they don't understand them. I think a lot of the time they do. But the people who make the decisions, who are sometimes politicians or senior civil servants, they often want yes/no answers. So I think in my opinion, it's all about communication. You know, it's all about communicating it and being transparent about the uncertainties and trying to show people that the forecasts are uncertain. They're never going to be 100% accurate, but they're still useful. But that's just my opinion.
No, I think you're totally right. The problem is sometimes we do want to tell about the uncertainties, be very transparent, and then the problem is how they accept it, right? I think Linda wrote a little bit about it, but because they really want, they kind of don't accept the huge uncertainties that we have, and we can't really just mask it out. So yeah, it's not only the problem that we don't want to show them, it's just that they don't want to see, sometimes they don't want to accept the uncertainties that we have to show them.
Yeah, I mean, and I think it's very difficult. And I mean, I experience this a lot in the work that we do. And I think there's a number of ways you can do it. You can have games with people. We've been doing some games showing related to probabilistic forecasts with some stakeholders we're working with. And, you know, just everyday examples. There's a probability when you cross the road that you might not make it to the other side, that you might get hit by a bus. I mean, it's unlikely, but nothing's certain in life. And I think it is challenging because people always want to know exactly what's going to happen in 5 days' time with 100% accuracy. Deal with it. The only way I deal with it is I say to people, you know, if I knew that, I wouldn't be doing this job. I'd be a millionaire because I'd know what's going to happen in the future. But I mean, that isn't very helpful, I know.
But that may help get the idea through. Thank you very much. Linda, would you like to say something? Okay. So I just, I think we have to close the debate right now, but we'll have the final debate to keep on with our really nice discussions. And this afternoon at 4, I have some of the speakers have already confirmed the presence. I think Linda will be with us. and also Angelica. But we also have Pierre Javel from France in RAE, Lionel Berthet, who is working chief of one of the operational services in France, Leandro Kazimierski, that asked some questions for you today, and he's from the National Institute of Water in Argentina. He will also participate, and also me, Karina Fruscio, Stefan Collett, and Harry Hendricks Franzen here from Jülich. But Darren or Marco, if you could participate, it would be really nice. You can still take part, of course.
Thank you.
And thank you very much for these really nice talks and discussion today. Thank you.
Thank you, everybody.
Thanks,